Joe James, and this is part 2 of the Python binary search tree. And this video is going to cover the remove function only. Remove is a pretty complicated process, so we're going to cover a variety of different cases. So the remove function basically takes a piece of data or an integer value, and it's going to either return true if it successfully removed that value, or false if it did not. So there are a number of different cases we're going to cover here. Someone calls the remove function on an empty tree, or if the value is in the root node, for example 15 here, if someone wants to remove the 15, value is not in the tree at all. For example, 3 is not in this tree at all. Or maybe someone wants to remove node with a value of 8, and 8 has only one left child and no right child. Or 19, which has only a right child and no left child. Or node 24, which has both a left child and a right child. So there are a number of different cases. We're going to cover each one of them in detail. First, we're going to have a couple of variables that we use throughout the binary search tree remove function. We have node, which is the node we locate that we want to remove. So if we want to remove 8, then 8 becomes node. And that node's parent, the remove node's parent, which in this case is 15. And we can see that node is a left child of node 15. 15 also happens to be the root node. And to locate node, we obviously have to descend the tree. We have to do a search for the node that you're trying to remove. So we locate that node by essentially doing a find. So let's say someone wants to remove a value from an empty tree. We are just going to return false. And if the value is not in the tree, if someone wants to return, for instance, a 3 from this tree, we can see there's no 3 in the tree. We just return false, because we're not able to remove that value from the tree. Now another instance, if someone wants to remove an 8 from this tree, and we can see that 8 has one left child. Now there are two different possibilities. If we have only one left child, the node that we're trying to remove has only one left child. One, this node that we're trying to remove could be a left child, or it could be a right child of the parent. In this case, we can see that 8, the node we're trying to remove, is the left child of its parent. And in that case, we can simply do parent.leftChild equals node.leftChild. In other words, 15's left child equals 5, right? That basically cuts node 8 completely out of the picture, and it promotes node 5 up to that spot. So even if 5 has a whole subtree below it of left and right children, we don't even care. We're going to move the entire node and its subtree, if there is one, up to where node 8 is by making 15's left child node 5. So node 8 is now cut out from the tree. It still exists out there somewhere, but basically it's not included in our tree anymore. The other case is where the node we're trying to delete has only a left child, and the node we're trying to delete is a right child of its parent. For instance, node 8 here is 5's right child, right? And it has only one left child. And we can simply do parent.rightChild equals node.leftChild. So parent, which would be 5, right child, which is currently 8, we're going to change this so that parent.rightChild becomes node.leftChild. In other words, we're moving the 6 up to where the 8 is, right? 5's right child becomes 6. So that solves the problem with the left child only. Now for the right child only, it's very similar. Now if we have a parent and the node we're trying to delete here is 19, node is a right child only, right, 21, and node is a left child of its parent. 19 is the left child of 24. We can simply do parent.leftChild equals node.rightChild. In other words, parent.leftChild, which is currently 19, becomes 21. So we move 21, and if it has a subtree, 21's whole subtree, up to where 19 is now by simply pointing parent's left child towards 21. And then if node is a right child of its parent, in this case, let's say 30, node 30 is a right child of its parent 24. We want to delete node 30. We can move 32 up to where 30 is. And we do that by saying parent.rightChild equals node.rightChild, or 30's right child. So 24's right child becomes 30's right child. Now let's say a node has both a left child and a right child. In the case of 24, we have 19 and 30. We have both a left child and a right child. And again, these can have whole subtrees. In the case of 30, there's a whole subtree down below. So the process here is a little more complicated. First, we're going to use two more variables. We're going to use a variable called del node, or the node that we want to delete, because now we're not going to delete node anymore. We're going to use del node to indicate the node that we want to actually delete, and del node parent as the parent of the node we want to delete. And how do we find this node that we want to delete? What do we do next? Well, we're going to start at node. We're going to find the lowest value, the smallest value, in node's right subtree. So we go to node's right child, and then we go left child, left child, left child, left child, all the way down to the bottom until there's no more left child. And then we reach del node. Next step is to move del node up to node.value. In other words, we're going to copy this 25 up to this spot here, up to node. Now we can simply delete node 25. We moved the value 25 up to here, so we still have a balanced binary search tree, but we're now going to delete node 25 because we don't want this duplicate value down here. So del node has to be deleted now. And this is pretty simple in this case because there's no subtree below it. We can simply say 26's left child equals none. But if there was a subtree below it, then we would go through basically the same remove process that we used previously. So if the value is in the root node, let's say we want to delete 15, and 15 is in the root node. There are a few different possibilities here. We could have a one-node tree, right? 15 could be the only node in the whole tree. So we'll do self.root equals none. In other words, we're saying this is now an empty tree. We deleted 15. Self.root is none. If value in root node has a left child only, so let's say 8, we would basically delete the 15 by saying self.root is equal to self.root.leftchild. So 8 becomes the new root node, right? And it's basically the same process for right child only. And the same process essentially really for both a left child and a right child that we used above. The only difference being that root node doesn't have a parent node. That kind of explains roughly how the algorithm works for the remove function. Now let me show you some of the code. Again, the remove function is taking a value called data. Our first check is whether or not we have an empty tree. If the tree is empty, then we simply return false. And our next check is if the data is in the root node, because if it is, we have special processing for that. Now we have a whole bunch of lines of code, probably 20 or 30 lines of code just to address this root node thing. I'm going to skip over that, and we're going to come back to that in a second. So let's scroll down. Now we're going to assume that we don't have an empty tree and the data is not in the root node. So now what we need to do is set parent equal to none, set node equal to self.root, and then we're going to ascend the tree, descend down the tree to find the node that we're trying to delete. We'll set node equal to that node, and we'll also set parent equal to that node's parent, and then we'll go ahead and delete the node. So the case 1, the data is not found. We simply return false. Case 2, the removed node has no children, in which case we can just set the parent's either left child or right child to none, depending on which side the node is on. Cases 3 and 4 are very similar. We have a removed node has a left child only, or removed node has a right child only. And again, we do one check, because there's two different cases here. If the removed node has a left child only, we do one check. We check to see if the node is a left child or a right child of its parent. And if it's a left child, then we assign the node's left child to the parent's left child, and if it's a right child, we assign the parent's left node to the parent's right child. And we do basically the same thing for the removed node when it has only a right child. And in our last case, the node we want to remove has both a left child and a right child. Now in this case, recall we need to descend down the tree and find a del node and a del node parent, which is the lowest value in the node's right subtree. Recall we showed this in the presentation above. So this while loop here finds node and del node parent, right? It finds the lowest value in the right subtree. And now that we've found that, we copy that value from del node over to node.value. This if-else statement is going to delete the del node. So we have different cases for the del node and different delete steps. So in the first case, it has a right child only. And in the second case, there are no children at all. We know that del node doesn't have a left child and it doesn't have two children because we've already descended to the bottom of the left child to find the del node. So that covers case 5. Now let's scroll back up and take a look at data is in the root node. Now if the data is in the root node, we have basically the same set of cases. The only thing that's different here is the root node does not have a parent. So we don't need to set the parent node to anything. We simply copy the value that we're trying to delete up to the root node. So if there is no left child and no right child, we just delete that node and set self.root equal to none, an empty tree. If we have a left child and no right child, or the next case is if we have a right child and no left child, then we can simply copy the left child or the right child up to the root node. And the last case is we have both a left child and a right child. What do? Well, we have to find the lowest value in the root's right subtree, and we set del node equal to that value and del node's parent, and then we go ahead and delete del node. So this while loop will find del node and del node parent. We copy that value up, and then we delete del node using this if-else loop. That pretty much does it for the remove function. It's fairly complex, so you should download the code from my GitHub site and try it out. If you have questions, please post comments below. I'll be happy to explain anything that's not clear. Play around with the code and watch the video again if you need to. That wraps up the video on the binary search tree remove function. I'm Joe James. Thanks for watching.